Dynamics, which is the study of motion and how mechanical systems move, is one of the core mechanical engineering classes. Current instruction of this class is very theory and textbook based, with students solving problems based on textbook drawn linkages and devices. With this project, we want to change how dynamics is taught by incorporating real devices into the study of dynamics. Our chosen method to doing this is by using inertial measurement units, or IMUs, such as this one. This is the inner workings of the black box of the IMU. Each IMU contains an accelerometer and gyroscope and measures acceleration and angular velocity when attached to a device. As you can see, its small size makes it very feasible for use in the classroom. The overall goal of this project is to develop class material based on a certain mechanical system so that while in class, the instructor can run an experiment on the device using IMUs, analyze the data, and then pose a homework problem to students based on the results. This wheel assembly next to me is our chosen mechanical system of study for this project. We considered many other devices based on their presentation of rigid body dynamics concepts such as a bicycle, a piston cylinder crankshaft assembly like the one in your car, and a pendulum clock, but ended up choosing this one because of its presentation of many dynamics concepts and its feasibility for use in the classroom. Experiments were run on this device with the IMU attached in the center of the wheel here. I will show you one such experiment. All of the devices needed for data collection with an IMU are present on the table in front of me. We have a computer, the IMU, a router used for communication between the computer and the IMU, and the wheel assembly. The first step for data collection involves the computer and the interface. This gives information about the IMU before, during, and after the trial. The next step is to turn on the IMU by removing the pin. Next, we need to wait for the IMU to communicate with the router, which can sometimes take a few seconds. After communication has been established, we can set the amount of time for each trial on the interface. We can also set how the memory is going to be stored. And as you can see, the IMU has established communication. Now, to begin the trial, we start by attaching the IMU to the wheel assembly. For this trial, we're going to study the oscillatory motion of the wheel with the extra mass of the clamp attached. We're going to start the clamp at 180 degrees and release the wheel from rest. Now we wait for our 10-second trial to complete. And now that our 10-second trial has completed, we can retrieve the data that was saved on the IMU. We do this by selecting the trial and retrieving the data. Like communicating with the IMU when the trial first started, this can also take a few seconds. After the data has been retrieved, as indicated by the status bar, we can save the data for use later to analyze it. And now that the data has been saved, we can use MATLAB to analyze the results and see what we just saw, what just happened. And this is the MATLAB result of the trial that we just ran. This is the data that was collected by the IMU during the experiment that we just saw. Angular velocity data is on the left and acceleration data is on the right. This data can be used in the development of problem statements, which is the last stage of this project. This is one problem statement based off the experiment we just saw. It asks the students to find the reaction forces of the bearings on the wheel assembly. This is not the only problem that this experiment can be used for. Students could also be asked to find frictional torque or analyze conservation of energy based on the results of this experiment. This problem statement, along with many others, all based on different experiments run on the wheel assembly, is the final compilation of results for this project.